Hello, in today's video we're going to be talking about percent yield. Now this is more of an industry-based type of terminology, and if you become a chemist out in the world and you go work for Dow Chemicals or Procter & Gamble, you'll be doing percent yields, and generally what will happen is the better your percent yields, the higher raise you're going to get. It means you're a better type of an experimental chemist, generally. So let's talk about what a percent yield is. Well, it's a new equation. The percent yield of a reaction is going to be equal to the actual amount of product produced, actual amount in grams, divided by the theoretical amount of product that could be produced. Amount. Then we're going to multiply it by 100% because this is a percent. So let's break this down. The actual amount is if you went into the laboratory, performed a reaction, and actually weighed your product at the end. That's considered your actual amount. The theoretical amount is taking your starting material, however many grams of starting material you have, going through stoichiometry, going through those balanced chemical equations, and predicting how much you should obtain at the end. So this number will generally be less than 100%. You're never going to be as good as theoretically predicted in most cases. So you're most likely going to get less than 100%. If you end up getting something above 100%, it means that you've accidentally introduced some sort of flaw into the system. You have extra water attached to your molecule. You accidentally swept in some dust when you were doing this reaction. Something went awry where you have extra weight added. So let's actually do an example of this using the same balanced equation that we used on the previous video, the combustion of methane. So we know that methane is a gas, plus we had the 2 O2, which is a gas. This yielded 1 CO2, which is a gas, plus 2 H2O, which is a liquid. And let's say that you were in industry and you started out with 3.0 moles of methane. Now, from this 3.0 moles, you actually burned it in an abundance of oxygen. What that means is this is not a limiting reactant problem. We have 3.0 moles of methane and an infinitely large number of oxygens, plenty of oxygens to actually allow this reaction to take place. Now you performed this experiment and you weighed the amount of water that you produced at the end of the experiment, and you obtained, let's say you obtained 104.2 grams of H2O after you performed this reaction. This 104.2 grams of H2O is considered your actual amount. The reason for that is you performed this experiment in real life, you weighed out your amount of water at the end, and you weighed out 104.2 grams of water. Now we have the actual amount, we need to figure out the theoretical amount. The theoretical amount will always use your balanced chemical equation. It's theory. You're using math in order to predict something. So we can start with our 3.0 moles of CH4. We can perform our dimensional analysis using the balanced chemical equation here. For every 1 mole of methane, there are 2 moles of water. The moles of methane cancel, we're into moles of water, but our actual amount was in grams, so we need to convert from moles to grams. For every 1 mole of water, there are 18.02 grams of water. That cancels those out. And we end up getting a value of 108.12 grams of water. So I'm trying to see on the screen if that actually showed up. So that's 108.12 grams of water. So now we have 2 different values. We have our actual amount and we have our theoretical amount. So what we can do is we can plug in our actual amount on the top and our theoretical amount on the bottom. Our actual amount obtained from experiment was 104.2 grams of water. Our theoretical amount was 108.12 grams of water. You'll notice the grams of water cancel. This is a unitless value except for the percent. If we multiply all this out, we end up getting 96.3744%. And if you followed all of the significant figures, this would only have 2 sig figs, and we would end up with 96%. This is a 96% yield. What that means is every time you perform this experiment, you can predict that 96% of your product is going to be made. So from 3 moles of methane, you've made 96% of the water that you thought you were going to make. So this is a simple example of limiting reactants. We're going to be able to do these forwards and backwards by the end of class tomorrow. That is all I wanted to say about limiting reactants, and I will see you all in class tomorrow.